Welcome. In this lecture, I'm going to talk about kind of congruence mod M representatives, right? So we're going to want to kind of divide up or partition the integers into these nice piles, kind of like you would with even and odd numbers. And then you kind of want to know how many piles that you need. Like, it's not a coincidence that congruence mod 2 is what gives you the even and odd numbers, and you need 2 piles. So let me just kind of explain to you how this works. Okay, so as in the examples, right, we're going to want to divide or partition, kind of, divide's kind of a funny word because it has another meaning, but it's okay. Here I just mean partition. The integers, see, right, and I'm going to want to use congruence, okay, into those congruent to so 0, 1, m minus 2, or m minus 1 mod m. And we can. Okay, so here's the proposition. I'll put it right here. Okay, so proposition. And I might refer to this by congruence representatives. Okay, so suppose that, and I'll write this and then we'll kind of talk about it a bit. Okay, so suppose that m is in the natural numbers, okay? Then we have that each k in the integers, so each k in the integers is congruent to, so congruent mod m, to precisely one of the integers zero, 1 up to m minus 1 mod m. Okay, so here's the proposition, and we'll kind of write all over it, as I tend to like to do, to kind of talk about it a little bit. Okay. So the first bit that we can like look at or talk about, so suppose m is in the natural numbers, okay? So this will be fixed but arbitrary. So this will be fixed but arbitrary, right? So that it works for all m in n. Okay, so what am I saying here? Which is that this, you can do this for any natural number. Oh, I kind of had decided I didn't want to, whoops. I had decided that I didn't want to use the natural numbers like this. I mean, I'm going to use instead, I've heard that one of the professors here uses z plus. I'm just going to do like z greater than 0. I kind of like that a little bit better, because then you can kind of alter what's there. Okay, so for any z greater than 0, you fix your m and this works, but it works for any m. Okay, what are some of the other pieces of here? When I say each k, so this part here, let's kind of talk about that part for a moment, which is that this is the same as, so here, I'm trying to figure out how to do this. Let's go like this. Okay, so this part here is the same as, right, saying for all k in the integers. So, you know, kind of symbolically, this is for all k in the integers. Okay, so we also, you know, this is also kind of set as fixed and arbitrary. Okay, so this is also kind of, so also set as fixed and arbitrary, because when we're proving this, so we're not going to prove this, maybe I will, because I want to make these videos that are posted kind of complete, but maybe not for a while. I actually kind of prove this because it's a bit long and involved. I'd much rather do it in person. But if you're proving this, this is fixed and arbitrary. So in some sense, you could think of, what do we have so far? Like, this would work for any integer greater than 0m and any integer k at all, okay? Once those are fixed, then the rest of the statement kind of follows that you're going to be able to take that integer and stick it into one of these bins, okay? So here's kind of the next part, which is that, so precisely one of, so how do we think of precisely one of, right? So this we can think of as, right? This part tells me here is that there exists a unique, right? So to prove, right, you're going to have to actually find the integer and then show that it works and show that it's unique. So to prove, you need to, you know, find/state the integer. Find in your scratch work, state in your proof. Right? And then you need to show that it works. And show it's unique. Okay? Now, that's to prove it, right? But you could also know that it already, like, if you, you also can use this, right, to say that, oh, okay, once I have my m and I have my k, then I know that it's going to have to fall into one of those bins. So you can also use that. But if you want to prove it, you're going to need to do this, okay? And then the last part was that, I didn't use orange yet. Have I? Yes, I did. I'm going to use, like, all my colors. Okay? So these integers like this. So what does this kind of part here tell me? Okay, so this tells me that it must be an integer. So must be an integer in, so there must be, right? So this integer that exists must be an integer in 0, 1, up to m minus 1. And this is kind of what it means that it works. So this works here is that it must be an integer in, so this is kind of going in both things. So it has to be an integer in here, okay? And then also, and that it's congruent to k mod m. Well, so it must be an integer in here, and that it's congruent to okay. So, like, to kind of say what's going on here, right? If you fix, this is going to work anytime you fixed for me a positive integer m and a positive integer k. And once you've done that, you're able to say that it's in one of these, and in precisely one of these equivalence classes, mod m. It's either equivalent to 0 or to 1 or to up to m minus 1. So this kind of allows us, just like you would with even and odd numbers, you can kind of divvy up the integers into those bins. You can kind of have this picture of these two, like, trash bins, and one of them says, like, even numbers, and one says odd numbers, and every time I give you an integer, I can just kind of toss it in the correct one. And now I have a bin full of even numbers, a bin full of odd numbers, okay? But then I can also do this with, if I'm looking at congruence mod 3, now I just need three of these trash bins, 1, 2, 3. And so I'm either congruent to 0 or to 1 or to 2, and I can just kind of stick it in. And then the 0 or the 1 or the 2 tell you which equivalence class you're in, okay? And so we are able to actually kind of divvy up our integers into these equivalence classes. Okay, so hope that made a little sense. It's kind of cool. Things are starting to come together. And I will see you in the next lecture.